There we go. Yep. All right, the last hurrah here. And sorry for the YouTubers, you missed all of the beginning stuff because I didn't put my microphone on. You know my style. I usually like to introduce something conceptually, give you framework, give you a general concept of what the topic is about, and then we jump into the math. I'm not going to do that this time. We're going to do the math first. Bernoulli and fluid dynamics and Bernoulli's equation, it's better to just start with the math, and then we will discover sort of the outcomes of this statement. Daniel Bernoulli was an Italian physicist, so he's already a good guy in my book. But what made him even better is a phrase that that he published actually in the daily version of like Facebook or TikTok or something. And he said, let's see if I can remember the exact quote, "The world would be a better place if there were fewer mathematicians in it." Now, the context of that quote wasn't that he disliked mathematicians. The Bernoulli brothers, and there were several, loved taking pot shots at each other in public. I try to imagine like their Thanksgiving dinners. It must have been pretty nasty. But Daniel Bernoulli had a brother who was a mathematician, and the mathematician brother and physics Bernoulli were constantly sort of at each other, right, over their theories and ideas and their mathematics and stuff like that. But I still like the quote. My apologies to all you math majors out there who I've just offended deeply. What was it that Bernoulli did for fluid dynamics? He came up with this statement, okay? And it starts with a pressure, right? So this is going to be a pressure equation. But this pressure equation is going to deal with fluids in motion. Up till now, all we've done is fluid statics, where fluids don't go places. They're just sitting there, whatever's going on, you swum to the bottom of the pool, whatever. The water's not moving, okay? So Bernoulli's equation is a pressure equation, but it includes the motion of a fluid. And that motion is captured in a term, 1/2 times the density times the velocity squared. Put a pin in that. We're going to come back to that. Plus, our kind of well-known pressure term, this rho GH, we've seen this before, often referred to as the static pressure, right? The pressure at depth is going to be, some pressure that's already there plus the static pressure. What Bernoulli has added is this term, right, that tries to capture the motion of the fluid. Well, he originally wrote, don't write this down, he originally wrote this as this all equals a constant. In other words, anywhere in a fluid, right, this equation is going to hold true, but this version isn't terribly useful for application. And so you're going to see me, I just wanted to warn you, because you'll see it like in the textbook, you'll see it on YouTube, they'll say it's equal to a constant. And they never tell you what that constant is, because it doesn't matter. It's a constant for that particular fluid and that particular fluid situation, right? So if it's constant throughout the fluid, you can take Bernoulli's equation, apply it to one point in a moving fluid, and then apply it at another point in that moving fluid, say two different pipes maybe, right? Two different sections of a pipe, and they'll be equal to the same constant. If they're equal to the same constant, what does that mean we can write? Well, we can just set them equal to each other, right? Plus rho GH2. I forgot to put an H1 on that one. So that right there is called Bernoulli's equation. Now, what are the units of the things on the left-hand side? P1, what's that? It's a pressure, so what are its units? Something, right? Pascals, hopefully, right? Could be, right? But work in pascals, you'll be safe, okay? Which means 1/2 rho v squared has to have units of pascals, right? We're adding these things together. We already know rho GH has units of pascals, right? So again, this is why I call it a pressure equation, right? It's an equation where everything here has units of pascals. However, this should be familiar to you in a way that, and not the actual symbols, but the feeling of the equation. What does 1/2 rho v squared feel like? It feels like kinetic energy, doesn't it? Right? Instead of mass, we have density, but that's okay. We're using density for sort of like the mass term in fluids, right? Okay. The 1/2 is there, and the v squared is there, right? It's almost like that's a kinetic energy term. Is it a kinetic energy term? No, it's a pressure term, right? But it has the feeling of kinetic energy. Rho GH, what does that have the feeling of? Yeah, like potential energy, right? Kind of like MGH. And even better, we have like an initial and a final, don't we? I wrote it down as 1 and 2, but energy initial equals energy final if there's no work other going on. This whole thing has the feeling of conservation of energy, doesn't it? So how are we going to approach problem solving here? Like we did conservation of energy, right? We need a 0, we need an initial, we need a final, we apply this, and we see what we can find, right? So we're going to do some examples of that. So we're kind of, recycling a little bit here, a problem-solving method, but applying it to pressure. And so if you want, and then probably this is more correct, you could say this is a conservation of pressure equation, right? Okay, but we're still going to use, kinetic pressure sounds weird, so we're not going to say that. This equation has a partner equation that, this is what it is, okay? It's called the equation of continuity. Equation of continuity. It's an important equation, but on the surface it seems, duh. What this equation is trying to say. Well, okay, let's do this. Let's discover. See if we can pull meaning out of all of the tools we have in physics at our disposal. Area. What units does area have? Yeah, like a length squared, a meter squared, right? And what units does velocity have? It's a meter per second, isn't it? So what are the units on the left and right-hand sides? It's a meter cubed per second. Now, a meter cubed, what is that? That's a volume, right? So this equation is a volume per time, right? We call a flow rate. And maybe it's a little bit easier of us to think of maybe in terms of gallons, right? So if I have a hose watering my garden or something like that, and at the house where the hose is connected, the water flow rate is, 5 gallons per minute, okay? What is this equation trying to say? Say point 1 is near my house, right? And point 2 is the end of my hose. What is the equation of continuity trying to tell us? The amount that comes out of the house has to come out of the hose. Right? Okay, what would make that not true? If there's a leak, right? Okay, so the equation of continuity says no leaks, right? But in any given situation where there are no leaks, okay, and by the way, we're doing perfect fluids here, not that they're massless, they definitely have mass, but they don't have turbulence in them. They do something called laminar flow. If you've ever watched the stream from a hose come out, it looks all nice and smooth and then it breaks up into droplets, or maybe from your kitchen sink as the water falls, okay? You have nice smooth laminar flow all connected, and then it breaks up into the individual droplets. That's called turbulent flow. So we're going to assume laminar flow. We're going to assume no turbulence in the pipe, all that sort of stuff. Then this equation of continuity is what I like to call the fire hose equation, or the I'm going to get that cat that's pooping in my children's sandbox equation. We've all done it. I'm not talking about cats. Maybe that's just me. You got a hose. You are watering something, filling something, doing something with a hose, right? And a target of opportunity appears. Could be little brother, little sister, somebody, right, that you have a vendetta against, whatever the case may be, okay, this target appears. You have a hose, not with no nozzle on it, right? You just have a hose. What do you do in order to get the water to reach the target? You put your thumb over the end, right? You're applying the equation of continuity. The equation of continuity says that if 5 gallons per minute is coming out of the house, 5 gallons per minute has to come out of the end of that hose. But what have you just done to the cross-sectional area of the hose by putting your thumb over the end? You've reduced it, right? So area 2 has gone down, right? So if area 2 has gone down, area 1, V1's whatever it is, right? Cross-sectional area of the hose, speed of water in the hose, right? Now area 2 suddenly has gone down. What does V2 have to do to keep the equal sign? It has to go up. So what happens to a fluid if it runs into a constriction? It speeds up, right? If you have a big fat pipe and you try to push water into a narrow pipe, the water in the narrow pipe has to speed up so that the volume flow rate can be the same in the pipes, right? That's what the equation of continuity is trying to tell us. Equation of continuity together with Bernoulli's equation, right, which is Pascal's on both sides, allows us to solve quite a few fluid dynamics situations. So let's apply them to some examples, okay? And then we'll talk about the concept or the phenomenon that falls out, because Bernoulli's equation and the equation of continuity are going to explain the following. $1,000 fines on the freeway. Cold legs in the shower, and how airplanes can go up. All of these things and more can be understood if we know something about Bernoulli's equation and the equation of continuity. Let's talk about a siphon. What's a siphon? Let's say we've got a big pool of water, lots of water. Could be a water tank, could be a pool, something like that. And we need to drain it, right? How could you do that without a pump? Get a garden, get a hose, right? Okay, and spend a week, right? But to get the water to flow out of the hose, I mean, you can't just like put a hose in here, right? And expect anything to happen. What do you have to make sure happens to the end of this hose? It has to be lower, right, than what? It has to be lower than where the surface of the water is, right? Okay. I wish I could demonstrate it to you, but they did not provide me a sink in this room, so it makes it kind of hard, right? But if you've ever sort of played with a hose in a pool or a tube, right, you know that you have to, if you try to raise the end up, the water stops flowing. It needs to be lower than the surface of the water. The amount of hose inside of the water doesn't matter. All that matters is that this part be underneath the surface in some way. Okay? So this is what we're gonna do. We're gonna find out how fast the water is flowing out the end of the siphon. Okay? if we assume that we know a few things here, right? So our goal is to find out speed of the water down here, right? What's the speed down here? That's what we want, okay? What do we know? Do we know anything about the pressure anywhere? What's the pressure right here? Atmospheric pressure, right? Pushing down on the surface of the water. Okay. What's the pressure where the water is coming out? It's also atmospheric pressure. I mean, we're not doing a siphon off the end of like Mount Everest or something, right? Okay. There's no appreciable pressure change under like even 100 meters. There's no real difference in the pressure. That's very important. Okay. So we know that the pressure there and there. Okay. In order to apply Bernoulli's equation, what was Bernoulli's? Is P1 1/2 rho V1 squared plus plus rho G. So I get excited about the 1/2. P2 plus 1/2 rho V2 squared plus rho G H2. Okay. So in order to apply this equation to our situation, we have to pick three things. What do we have to pick? Got to pick a zero, right? We have a term rho GH that's acting like potential energy, and so we have to like be able to pick. This isn't that weird potential energy from chapter 13, right? We're back to like normal. G's not changing. Fluid dynamics from outer. No, that's not good. That's not good thought. Okay, so where's zero? The lowest point? That's kind of what Mr. Balogh kind of always did, right? Put zero at the lowest point, okay? Now we need like a 1 and a 2, an initial and final. Where are we going to pick point 2? Where are we going to pick our final? Remember, you always put a point where you're trying to find something, right? Where are we trying to find something? At the bottom, right? So I'm going to call that the final or point number 2. Okay, since I'm using 2's here, I'll call this point number 2. Since I'm using numbers, I'll call that point number 2. Okay, so now we need to pick a point somewhere else in this system. And it could really be any point, but ideally it will be a point where I know something. Where's our other point going to be? Surface of the water. Right? We might know how deep the tank is and all that kind of stuff, but if we know that a siphon functions based on like where the surface of the water is. So kind of a natural point to pick. It could be a wrong point, and we'll figure that out later, but like it seems kind of natural that we would just pick the surface of the water because we kind of know what's going on there. All right. So now what we need to do is we need to see if we can apply this equation and see how many knowns and unknowns and all that kind of stuff that we have as we go along. So let's ask some questions. Do we know the pressure at point number 1? Yeah, we do. Do we know how fast the water is going at point number 1? Not given. Do we know the height? I keep forgetting my 1. Do we know the height of point number 1? It could be measured, right? We have now picked a 0. So what is the height going to be? It's going to be whatever the vertical distance is between the surface of the water and where the end of our siphon is. Okay? So supposedly maybe we could know that. All right. Do we know anything about the pressure at point 2? Yeah, same as point 1. Do we know how fast it's going at point 2? No, but we want to find it, right? We want that to be unknown so we can solve for it. Do we know anything about the pressure at point 2? Or the height at point 2? Yeah, what is it? Okay, that's 0 because height is 0, right? So what are we left with? We're left with V2. That's what we want to know. We'll assume that we can measure the height, okay? We're going to know how far below our siphon is. But that leaves V1, right? Now I ask you, if you have a swimming pool's worth of water and a garden hose, how fast is the surface of that water going to be moving as you drain the pool through a garden hose? Hardly anything, right? It's going to take days to do this, right? You have to go get special permits and let the city and county know that you're doing it so that you don't overwhelm the drainage system or whatever, right? Okay, but like, it takes days, okay? And the bigger the hose, the faster this is going to go, right? But if you're just doing a garden hose, effectively, like the water is going to be coming out of the end of this hose at, meters per second type velocities. But the surface of that water is going to be doing like, I don't know, centimeters per hour, right? Just really, really slow. So what can we kind of say about the speed of the water at the surface? Yeah, it's pretty much zero. We're just going to kind of make that assumption here. Big tank of water, very tiny hose. It's going to be zero. Another way in engineering speak to make this happen is to make sure that you are filling the tank as fast as you are draining the tank. Why would you do that? Why would you want to have a tank of water that you're both filling and draining at the same time? What possible use could we have for that? Water towers. What's a water tower? It's a tower of water. It's a big tank that has been put up in the air. They are not for water storage. This is not a good plan. Okay? Does anybody know what water towers exist for? To make water pressure for the town. Okay? By putting a bunch of fluid way up high, we get rho GH, right? Height, which causes pressure. And pressure is what is needed to push the water into all the houses, right, in the town. Towns that don't have water towers have water pumps that are causing the pressurization. Okay? But a water tower provides pressure. But in that case, with the 5,000 gallons that's up there, right, you want to be putting water in as fast as you were putting water out, right? Otherwise, you can't maintain your water pressure. Okay, so is it safe to say that this first term here is zero? For all practical purposes, we've kind of set up an argument where we're saying, yeah, it's moving really slow. It can move a little bit, but we're just going to not worry about that. Okay, what do we got now? We got to solve for V2, right? Now I'm doing math. Why can I cancel these two pressures? They are the same thing, aren't they? Okay, and so they cancel each other out. I'm left with rho GH equals 1/2 rho V2 squared. I'm gonna reverse that so that it's not, I'm solving for the thing on the left. That's what all my teachers taught me. So I'm just going to reverse it. No strange math has happened there. I dropped the 2 because I'm just solving for the velocity coming out the end of the pipe, the hose, right? Okay, so what now cancels? Aha! Water, honey, or oil. Well, it does matter. Viscosity is a thing, but we're going to not talk about that. What do I do with the 2? Multiply both sides by 2, and then the square. Take the... What the heck? What just happened? Where have we seen the square root of 2GH before? Like everywhere, right? Like we got this when we did conservation of energy. We asked the question, right? How fast is something going when it lands, right? If you just drop something, okay, what is the speed it's going to have when it lands? Square root of 2GH. If you roll something down a hill with no friction and you let it go at 0 initial velocity, how fast is it going to be going at the end of the hill? If you drop a Ford Bronco off a cliff, square root of 2GH. What's it doing here? What question did we ask? How fast is water going when we drop it through a height h? What's the only answer we could have gotten? Square root of 2GH. I made a joke back then. I was like, if you don't know the answer, just put down square root of 2GH. Several of you are putting quan down. You're getting zeros for those. But square root of 2GH. What is gravity doing here? What's causing the water pressure in the first place? What's causing the height difference? It's gravitational forces, isn't it? Gravity's pulling down on the water. What does gravity like to do to all objects, regardless of their mass? Pull them at the same rate. This is one of those moments in physics where our arrogance kind of comes out. We're kind of pleased with ourselves, right? We're kind of like, look what we did, right? It should come as no surprise that if we ask the same questions in a different context, that we're going to get the same answers. It's kind of one of these flags that tells physicists, like, you know what? We might be on the right track when it comes to trying to understand how this universe works. Whether it's fluids, or penguins, or bowling balls, or we don't drop ladders, or Ford Broncos, we end up with the same results. If you're not sure what the answer is, try the square root of 2GH, right? Okay. If it's gravity, right? Square root of 2GH. All right. So there's our siphon applying Bernoulli's equation. Let's do another one. Okay. This isn't something that we are terribly familiar with here in Fresno. The lack of multi-story buildings being close to each other. I mean, I know there's downtown, but it's not like Manhattan or Chicago or some of these other cities where they put skyscrapers like literally a street's width apart from each other, right? So you know the equation of continuity. What happens when, say, a 50-mile-an-hour wind, which is very typical for like a nor'easter, a weather pattern that exists in the wintertime, starts blowing snow through the city, right? If you're moving 50 miles an hour and all of a sudden you hit an obstruction that forces the air to go into a smaller area, what's that fluid going to do? It's going to speed up. And so it's not uncommon in large cities for the wind speed between buildings to get up to and exceed 75 miles an hour. 75 miles an hour is a very magical number. Does anybody know what 75 miles an hour is? No, it's because we don't have weather in Fresno, right? What we have is heat and bad air, right? We know all about AQI, right? The air quality index, right? But we don't know about weather. 75 miles an hour is a hurricane force wind. That's where you get, when a hurricane is a hurricane, it's because it has sustained winds of 75 miles an hour or greater. So it could be possible to get some pretty fast wind speeds between buildings, 80, 90 miles an hour, not terribly uncommon. So what's an engineer to do? Besides like designing the building to stand up, what's another thing you want to make sure doesn't happen to the windows of your building? That you don't want them popping out, right? Because if they pop out, where are they going? Square root of 2GH, right? So we want the windows to stay in the building. So let's get a little bit of let's get a picture going here. This is a window, but this is the side view of the pane of glass, right? And it's in the structure of the building, and we're going to call this side the inside of the building. And I got a little bit excited about my building edge there, right? And then we've got like the outside of the building. And this could be multiple stories, right, above the road. Okay, so there's our pane of glass, right? There's us, right? And we know that the airspeed, right, blowing around out here, they tell us is 11.2 meters per second. It's actually kind of blowing past the window, not away from it, but get the idea, right? What do we know? We know it's we know that the window itself, right, says it's a 4 meter tall window and 1.5 meters wide. Okay. They tell us that there's a difference in pressure. All right, we got to find that difference in pressure so that we can find the net force. Are force and pressure related to each other? Yes. We learned this at the very first day of fluids, didn't we? Pressure is force divided by area, isn't it? So if we can find the pressure difference, right, and we multiply by the area of the window, we can find the force that's acting on that window, right? So if it's a pressure difference, a delta P, then that's going to be like a delta F, the amount of force that is pulling on the window. Okay, so let's see if there's anything else we can kind of make an assumption. They don't explicitly tell us this in the problem, but can we make some assumptions? I'm looking for zero things. I'm looking for a way to eliminate things from Bernoulli's equations so I don't have to deal with them. We know the velocity on the outside. Oh, let's get Bernoulli's equation down just so we can think about its parts. Plus 1/2 rho V2 squared plus rho GH2. Okay, are there any things that I can do to like eliminate parts of this equation here? What do we know? So far, what do we know in Bernoulli's equation? Oh, okay. So I heard little bird tell me the height difference. So we have to have 2 points. What 2 points are we going to compare? What jumps out at you? Inside and outside the window, right? Okay. And if we put those at the same level, call it 0, then what is H1? 0. And what is H2? Also 0. And it doesn't matter if we put 0 there, because if we put 0 at the ground, this still, inside and outside, is at the same height. And if you have the same numbers on either side of an equal sign, what do you do with them? You cancel them out. That's nice. Okay. The 11.2 meters per second, where does that go? It's V2, isn't it? Speed of the fluid on the outside of the building. Okay. Which means that we're going to need to figure out what V1 is. What would V1 be? Where would it be? It's on the inside of the building. Yeah. How fast is the wind in this room? It's 0, right? Now, is there a little bit of air movement? I mean, the air conditioning's going if we listen really hard. White noise, right? We can hear the air moving through the ducts and stuff, but effectively, like compared to the outside, 11.2 meters per second is like 25, 30 miles an hour, okay? So there's no air movement in a building, right? Nobody's getting blown over by the air movement in a building. So we're going to call that 0, right? Okay, that leaves pressure 1, pressure 2, right? Which you would think like the inside of a building would be at atmospheric pressure, right? And you would think that the air on the outside of the building would be at atmospheric pressure. And that would all be true if there wasn't any fluid movement. But we have fluid movement around the outside of the building, so there is going to be a pressure difference here. In fact, buildings are often pressurized either positively or negatively, depending on what you're trying to do. Positive air pressure means that air comes in, and when you open a door, the air goes which way? Out. Okay? And if you do a negative air pressure in a building and you open a door or window, which way does the air come? In, right? Depending on the circumstance. This building, unfortunately, is pressurized negatively, meaning that when we open any door, which way is the airflow? In, which means all the cold air comes in. You remember how cold this hallway used to be back in January? Okay? And now the building gets kind of warm in the hallways. I want to throttle the designer of the HVAC system in this building. You never pressurize negatively in Fresno. You pressurize positively so that when you are doing air conditioning and somebody opens a door, what happens? The air in the building stays cold. You also filter the air because our air is unbreathable. That's a different story. Okay, so let's solve, what do we got? P1 plus 1/2, the V1 is 0, isn't it? I just argued that. I don't want to have to write it down. Equals, boy, that's a bad equal sign. Equals 1/2 rho V2 squared, and I forgot my P2. Okay, so let's solve for this pressure. We need this delta P, don't we? So P1 minus P2, I just move that over, equals 1/2 rho V2 squared. If you have well, in this case, an initial minus a final, it doesn't really matter. This is a delta P, isn't it? A delta is a difference between things, okay? And what are we now saying that difference in pressure is going to be caused by? The movement of the air outside, right? What are we going to put in for our density? Density of what? Air, right? That's the fluid that's moving. We know the speed that it's going, okay? And away we go, right? We can calculate this. I dumped it in, and I got a difference of 81.5 pascals. So again, this isn't the pressure outside the window. This isn't the pressure inside the building. What is this? The difference in pressure between the inside and outside of the building. So if that's the difference in pressure, can we now find the net force on the window? Is the window being pushed in by the air pressure on the outside of the building? Like, assume the wind isn't going or anything. Totally static situation, right? Is there a force on the window from the outside? Yeah, there's air, there's a fluid there, right? Is there pressure on the window from the inside? Yes. If the pressures are equal, then what is the net pressure on the window, the total force on the window? 0. The net pressure is 0, the net force is 0. What we have found here using Bernoulli's equation is a pressure difference. And if we were very, very careful in our calculations, we would have found that pressure difference, P1 minus P2, is positive number. Which of those two pressures is higher? If you have P1 minus P2 and you're subtracting two numbers and you get a positive number, which number was bigger? P1. The pressure's bigger on the inside of the building. The pressure's lower on the outside of the building where the wind is blowing? Hold that thought. We're going to come back to it. So what direction is the force going to be? If the pressure's bigger on the inside than outside, which way is the pressure going to be? Outside. So the window, if it's going to come out of its casing, is going to go which way? Out. Street side. Not in. Okay. So If it's 81.5 pascals, how do I find the total force on this window? Net force on this window. I need the difference in pressure, which I now have. And what's A? Area. Okay? So how do I find the area of this window? Yeah, 4 times 1.5, whatever that is, right? Gets me a difference in force, a net force of 1,960 newtons outwards. And since a newton is about 1/4 of a pound, and that's about 2,000 newtons, what's 1/4 of 2,000? 500, isn't it? So around I rounded quite harshly there. It's about 1/5. A newton's about 1/5 of a pound. But still, like, we're in the neighborhood of hundreds of pounds of force on this window, right? Which is substantial. Now, glass, depending on the kind of glass it is, can totally handle that. But the casing that holds the window in place needs to be able to withstand hundreds of pounds of force, right? Pushing out. In fact, if you ever get to see footage of like hurricane damage in cities, you'll see like high-rise hotels in Florida, high-rises in New York, that kind of stuff. After the hurricane's gone through, the glass is all gone. And in the hotels, all the beds, all the curtains, all the drapes, all the lanterns, everything, where is it? It's outside. Why is it outside? It got sucked outside. The pressure was lower outside. The glass has been pulled off and it's shattered in the street. Okay? Everything that was inside the room anything loose has been pulled to the outside balconies and the street level. When you design a house to withstand a hurricane, you don't want the roof coming off. You bolt the roof down. They actually call them hurricane straps. Okay? They're annoying, okay? But they will keep the roof from coming off because the pressure inside the house is atmospheric pressure. But if you have a 110-mile-an-hour wind going over the top of the roof, the lower pressure's on the outside. Which way is the roof going to go? It's going to go up, right? So that pull from that fast-moving fluid is the destructive force of a hurricane. That accompanied with the storm surge and the flying material that's picked up by those tremendous wind speeds, acting like bullets running into things. Tornadoes are even worse because their air speeds are even worse. But I'm alluding to something, okay, that needs to be thought of in design as well as engineering. This particular building, which I believe is in Shanghai, China, when they originally started designing it, they realized it didn't have the hole in it. And they realized that the building was going to be aerodynamically bad. And so to fix that problem, they decided to put a hole in it, and then it became a major tourist icon thing, blah, 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 right? You can marry design with engineering to solve a problem and make it beautiful and interesting and all that kind of stuff. But this has led us to a concept, an idea called Bernoulli's principle. And Bernoulli's principle on the surface seems backwards, but I've just given you several examples of where it appears. Bernoulli's principle says that the faster a fluid moves, the lower its internal pressure. I'll say it again. The faster a fluid moves, the lower its internal pressure. And let me tell you why your brain is kind of kicking back on this one and saying, that doesn't sound right, Mr. Balogh. If I came in with a garden hose and I started squirting all of you, you'd be mad, right? You'd be wet, you'd be mad, okay? But no harm done other than being wet. If I grabbed the fire hose and started squirting you, now not only would you be mad, you'd be hurt. Okay? Why? The pressure in the fire hose is a lot higher. It's kind of the whole point, right? You want water to go far to put out a fire, so you don't have to stand near the fire to put it out. So, Mr. Balogh, you just said that the faster a fluid moves, the lower its internal pressure. I keep using a word. What's the word I keep using? Internal. Okay. This is internal to the hose, right? It assumes laminar flow, all that kind of stuff. But the pressure you are thinking of when you were thinking about like fire hoses versus garden hoses is the pressure of the water striking something else. You have a pressure washer, okay? You're using the high pressure of that water in order to clean off the surface, right? It really gets the grime off. The pressure coming out the end of a pressure washer, right, causes that cleaning effect. That is a conservation of momentum problem. That's a chapter 9 problem. We're talking about the impact of water molecules on a surface, right? I'm not talking about that. I'm talking about the flow, the laminar flow of a fluid in a pipe or around an object. The faster that fluid moves, the lower its internal pressure, and I'm going to prove it to you. This is something you can do at home. Okay? Okay? What I'm going to do is I'm going to take 2 pages of my notes, right? And I'm going to hold them so that they are, an inch apart, a couple centimeters apart. Okay? You can make them as close as you want. But if you get them too close, they tend to just sort of stick together through static electricity. And then you want to hold them in such a way that they're vertical, okay, and close together. And the way I do this to sort of help myself is I'll grip them with my fingers like this, and then I'll put my thumbs together to sort of steady the whole thing. And you can do it hanging down. It's probably easier to do it hanging down, but I'm going to do it up like this so you guys can see what's going to happen. And I'm going to blow in between the pieces of paper, right? Correctly, right? I'm going to hold them together. I'm going to blow really quickly between the pieces of paper. If I pass out, it's okay. I just have asthma. Just kick me. I'll wake back up again. Okay? So I'm going to blow between the pieces of paper. I want you to watch what is going to happen. I didn't move. I didn't move my fingers. Do you see what's happening? What happens to the pieces of paper? They smush together, right? They come closer together. You try it, right? Maybe in the privacy of your home. People don't think you're already weird. You've been a physics student for a semester. You're marked, okay? So, why? Why did the pieces of paper squeeze together? Where was the lower pressure? It has to be inside. Pressure outside, air pressure, not moving anywhere. Fast-moving fluid between the pieces of paper. Bernoulli's principle, which comes from Bernoulli's equation. We just solved it, right? When the fast-moving fluid is on the outside of the building, where's the lower pressure? It's outside the building, right? The faster a fluid moves, the lower its internal pressure. I gave you 3 examples of things that could be explained kind of near the beginning of this lecture. Does anybody remember what one of those examples was? Airplanes. Okay, let's talk about how airplanes fly. This is a topic I love. I love airplanes and flight and all that kind of stuff. I'll do it on the iPad. I'm going to attempt to draw the cross-section of an airplane's wing. Okay? This is a crude approximation of what an airplane's wing kind of looks like. Okay? And the key thing about an airplane's wing, okay, again, in crosses, like we cut the wing in half and we're kind of looking at it. So like the wing is pointing in and out of the screen. Like the rest of the airplane parts are over here. Right? And there's a person inside the window looking out. You get the idea, right? Okay? This is the limit of my artistic ability. So this airplane wing, right? Okay? What's one thing that we need in order for an airplane to fly? Besides wings. What does the airplane have to do? It's got to move. Move how? Fast? Slow? Not at all fast, right? Airplanes do not fly by flapping their wings. Okay? Birds fly by flapping their wings. Airplanes don't. Okay? What airplanes do is they fly fast, right? Got to move. Anybody who's been in an airplane knows there's that exciting period of acceleration at the beginning, right? You get pinned back in your chair, all that kind of stuff, right? So how is it that an airplane wing generates lift? So there's a stream of air that's coming in, right? As the airplane pushes through the fluid. The stream divides. One half has to go up over the top of the wing, and the other half goes underneath the wing, barely deflected at all. In order for it not to be turbulent flow, the air splits here and comes back together on the trailing edge of the wing. A stall is basically when you've got too much turbulent air flowing over the surface of a wing. So what we have, okay, is a case where the top flow has to move over a larger distance in the same amount of time. This top path is longer than the bottom path. So if it has to travel a further distance in the same amount of time, what can you tell me about the velocity of the air over the wing compared to under the wing? It's faster, isn't it? Okay. This is faster. This is slower. Where is the low pressure? It's on top. Your low pressure is here. Your high pressure is here. The direction of net pressure is which way? Up, which means that the net force is up. How do you find the force? What's the area of your wing, right? The heavier a plane, the larger its wings needs to be in order to generate enough force to cancel out the other force that is trying to get the plane to do what? Come down. Square root of 2gh, right? You don't want square root of 2gh as your landing speed in an airplane. It's not a good day. So airplanes take advantage. Now, okay. For any engineer that might watch this on YouTube in the future or whatever, okay, I am required to say that I have grossly oversimplified how airplane wings work, okay? There is a lot of fluid dynamics that is happening around an airplane wing, okay? But at this level, at this stage, it's enough to say Bernoulli's principle is helping, is one of the primary causes of airplane lift. That allows airplanes to go up. If you want an airplane to go down in a controlled manner, what do? You slow down. Because the slower you go, the less pressure. And if you can manage to get the force pointing up to be a little bit less than the gravity pulling down, what's your plane going to do? Gently descend, right? Okay. So planes will slow themselves down in order to descend. Not stop, because if an airplane stops, what happens? Free fall, right? Okay. Now, my wife doesn't like taking airplane trips with me anymore because I can't help myself. Okay, number one, window seat, best seat. Okay. Window seat near the wing, not like the overwing exit row because you can't stow any of your junk or whatever, but like where I can kind of see the wing and the engines and all the important bits of an airplane that aren't supposed to fall off. And are where all the exciting... you can look out the window and look at all the ground down below. Boring people down there. Okay. But like all the cool stuff is happening near the wing, right? The flaps, the ailerons, the sharklets, all kinds of stuff going on. And my nose is like smashed up against the window as I'm watching the takeoff roll, right? Okay. And then as we start moving, I like start hitting the person next to me in the seat, right? Like, look, you have to see this. Bernoulli's equation is working again. And then there's this golden period during the takeoff below 10,000 feet when you have to have your seatbelt on, nobody's allowed to get up. I now have a captive audience for the person in the seat next to me, right? I can teach them all about Bernoulli's principle and it's so good, so good. My wife has heard that lecture too many times in her life. All right, so that's how airplane wings work. in a basic sense. Does anybody else remember what one of my examples was? What was that? $1,000 fine on the freeway. How is Bernoulli's principle involved with $1,000 fines on the freeway? Let's say that you have your study group, right? Your study group is formed. You guys have been into physics for a while, and you need sustenance, right? And then somebody says, "Oh, I could use some In-N-Out right now," and somebody else goes, "Oh, In-N-Out," and you say, "Okay, everybody, give me money. I will go pick up In-N-Out. Right? Get your orders in. We'll go do it." And so you drive to maybe the In-N-Out on Ashland or something, right? And you pick up the burgers and the fry. I apologize to any vegetarians in the room for this example. But you pick up the burgers and the fries, right? And you're on the way back to wherever the study group is, and you've got the burgers and the fries, and they're all sitting there in the front seat, right? Can you smell it? The smell of that French fry, right? And the beef in there, and the cheese, and the onion, right? And In-N-Out is like pushing every evolutionary pressure, right? Fatty, salty, protein, right? Like, good stuff, right? And so you're driving along, and there's a one of those French fries is kind of hanging out a little bit from the packaging, right? And nobody can blame you for taking one, right? Okay? Nobody can blame you because you're the one picking up the food, right? They didn't pay you for gas. So nobody's going to know. Nobody's going to know if you take a French fry, right? What happens next? Nobody's going to notice a second one or a third one. And before you know it, right, you've gone through 3/4 pounds of meat and probably 10 potatoes and whatever, right, okay? And you have you've lost it. You pigged out. It's the stress of finals. Mr. Balogh made me do it. And now, because your 1/4 pound of meat comes with about 4 pounds of paper, right, you now have loose bits of paper all over the inside of your car. You've got the meat sweats. And you decide that your air conditioner just isn't cutting it, and you're going to roll the window down. And you're on 41 or something, right? Well, you roll that window down, where do all those loose bits of paper go? Out. There's your $1,000 fine. Why do things tend to get sucked out the window of a moving vehicle? Anybody that's carried balloons around for a party and made the mistake of opening their window knows this. Why? Where's the fast-moving fluid? Outside? I mean, Mr. Balogh, I'm the one doing the moving. Shouldn't the air inside the vehicle be the fast-moving fluid? Well, no, you're carrying a static fluid at high speed, but the fluid itself isn't really moving, right? The fluid around the car is the thing that's moving, and so the low pressure is going to be where? Outside the car. $1,000 fine for littering on the freeway. But Bernoulli made me do it. The police officers don't understand. Cold legs. Oh, before we get to cold legs in the shower, let me just show you this. This is a Bernoulli device. It's not a leaf blower. It's a Bernoulli device. Okay, because ostensibly you're supposed to use it for blowing leaves around, right? But what comes out this end? A fast-moving stream of air, right? Okay. Okay. I have a ball, right? And so what should happen if I put the ball in the fast-moving stream of air? It will disrupt it, won't it? Where will the air be forced to go? Around it, right? So we're going to have a bunch of fast-moving fluid around the ball, and a bunch of static fluid not doing anything. Where's the low pressure? Wherever the ball is. I won't be able to talk with this because it's going to be loud. But have the force. It did, like, when you do it straight up and down, it's like, well, the air is pushing it up. But when you get to the side, right, it's like magic. It's not, it's science, right? Like, again, there's more going on here than just Bernoulli's equation, Bernoulli's principle. There's other very complicated effects and interactions that are going on and turbulent forces that are, but that's beyond us at this point, right? The point is, Bernoulli's principle tells us that the faster a fluid moves, the lower its internal pressure. And that brings us to cold legs in the shower. There are two kinds of people in this world. Those people that take showers in the evening and take them in the morning. We're not going to get into that argument, right? Okay? I guess the other part is the people don't take showers at all, but we don't like you. So there is some, for the sake of this example, let's just say that it's morning time. You need to take a shower in the morning. And I don't know about you, but I am not alive when I wake up. Just some sort of automaton, right? Okay? Nothing's quite good. Some people need a shower. Some people need coffee. I just need the blood to start moving in my brain, right? And the older I get, the slower this process happens, right? But let's say you wake up, okay, and your first act of the day is to go get in a shower so that you could actually wake up. I can tell by the look in your eyes that many of you understand what I'm talking about, right? So you are, by all counts, inebriated, right? Because your brain is just not connected to your body and things aren't working right. And so you probably have some ritual or method for turning on the water in the shower, okay? It might go something like this, right? You get into the shower, you close the curtain, right? And there is this conundrum that requires too much thought for somebody that's just woken up. But you have to be able to turn the water on with the shower pointed directly at you, right? Okay? And it only occurs to somebody who's awake that you could turn the shower on before getting in. But you're not awake, you're in the shower, right? Okay? And so you have you turn this thing on and then you've got some sort of funky dance that you do, right? To avoid the stream of water, okay? Because it's too cold and you wait for it to warm. Okay. You're standing there waiting for it to warm. You finally get into the shower. Oh, it's so low, it's warm. Oh, I'm waking up, all this kind of stuff. When the cold, clammy hand of death reaches out and grabs your leg, the shower curtain has attacked. You know of what I speak, right? You turn that shower on and the shower curtain billows in, right? You're like, come on, man, I need some personal space here, right? And the shower curtain is coming. There's all this room in the bathroom. Nobody's using that out there. Why can't you go that way? Why is the shower curtain attacked? Where is the fast-moving fluid? It's in the shower, right? You've got water that's pulling the air along with it, right? You've got faster moving fluid inside of the shower. Where's the fluid that's not moving? Outside, the air outside the shower curtain. Which way is the shower curtain going to go? Towards the low pressure, towards you. That's why when I became a homeowner, I made sure every shower in my house had doors. I didn't want to hear screaming in the morning, right? Door's not going to go anywhere. In hotels, they'll do a trick. So here's a bathtub, okay? They'll put the shower, like the bar that holds the shower curtain, they'll kind of put it like away from where like the vertical plane of the edge of the thing is, the tub is. And I'm exaggerating this quite a bit, right? But that forces the shower curtain to kind of hang like that. Sort of a cross-sectional picture here, right? If it's kind of out, two things happen. Number one, they can advertise that they have spacious tubs. The size of a bathtub is set by like standards in construction and all that kind of stuff. All bathtubs are pretty much the same size, with some exception. But especially in big construction, they're all the same size. So they haven't changed the size of their tub. What they've done is psychologically tricked you into thinking that it's bigger because the shower curtain is kind of further away where your head is, right? It's still just as close to the edge of the tub, but by putting it out there, they've opened it up, made it a little bit more spacious. They can charge more money for their exclusive, right, bathtubs. The other thing they've done is they've made sure there's a component of gravity acting on the center of mass of the shower curtain that's pulling the shower curtain away, right, from the tub. If your shower curtain's hanging perfectly vertically, then gravity's just pulling down, right? And Bernoulli comes along and tries to push it sideways. There's no component of gravity that can help, right? If you've tilted it at an angle, right, you can keep the shower curtain from coming in and getting you. Or just get a door on a shower, because that's doors. Anyway. Bernoulli's principle in connection with the equation of continuity and Bernoulli's equation is the very first little tiny bit of sand on the beach of fluid dynamics. Computational fluid dynamics, CFD, is why supercomputers were invented. It is the mathematics and physics that drives weather forecasting and trying to understand what's going on in our atmosphere. To figure out how cars and planes can be more efficient in their shapes. You do computational fluid dynamics, which requires a lot of differential equations being solved simultaneously, and this is something that computers are very, very good at, right? Doing the same kind of calculations over and over again to figure out what fluids will be. Fluid dynamics is a wonderfully complicated, absolutely amazing branch of physics and engineering that I won't touch with a 10-foot pole because I am dumb. And the people that do CFD are like, oh my gosh, amazing. It makes orbital dynamics look really, really easy. So along with electrical engineering, it's one of the, and organic chemistry, it's one of the things I will simply not do because I don't have the chops for it. That's it. I have nothing left to teach you. That's not true. But as far as this class is concerned, we are done. I want to thank you for an excellent semester. This has been so much fun. You guys brought energy in a way that I don't think I've seen since the pandemic, right? So congratulations, you're learning to talk to each other again. That's good, right? But seriously, it's been an entirely fun semester. As many of you know, I am not teaching the 4 series next year, but I will be here, right? So you just need to come to GRASP on Fridays. I'll give you a big hug and I'll help you through it, right? Because you can do 4B, you can do 4C, because you've done 4A. I will see you tomorrow for the review.